Good morning, doctor and everyone. We are from Group 6 are going to present about chapter 13, 14, 15, which is rolling, forging and extrusion process. Before moving to our presentation today, let us introduce ourselves. My name is Vinoshan Gunalan and my metric number is 230554.
Hi, Assalamualaikum. My name is Adam Muhazif bin Aminuddin and my matrix number is 228080.
My name is Dushan Alalaki Tanasega and my matrix number is 228773.
My name is Anandarao Analaki Ishwarudu. My matrix number is 229435.
Now let's look at the introduction. What are bulk deformation processes? Bulk deformation processes are metal forming operations in which the workpiece undergoes large plastic deformation under the action of primarily compressive stresses. This process causes significant changes in the shape of the material while maintaining nearly constant volume and without intentional material removal. The key characteristics are deformation occurs beyond the elastic limit, resulting in permanent shape change. Material experiences high compressive stresses, which reduces the likelihood of fracture. It's capable of producing large reduction in thickness or major shape changes. It can be carried out under hot working conditions, which is above recrystallization temperature, and for cold working conditions, which is below recrystallization temperature. Common bulk deformation processes, which are rolling, which reduction in thickness by rotating rolls. For forging, which shaping by compressive forces using hammers or presses. For extrusion, which forcing material through a die to obtain uniform cross sections. Moving on to engineering relevance and stress strain behavior. Engineering relevance of bulk deformation processes. Bulk deformation processes are widely used in manufacturing because they are enable the production of components with superior mechanical properties, high productivity, and low material wastage, making them ideal for mass manufacturing applications. First, for strengthening mechanisms. Plastic deformation causes grain elongation and refinement, improving strength and toughness. And the cold working results in strain hardening, leading to increased yield strength and hardness. Directional grain flow improves fatigue resistance and load bearing capacity. Next, for manufacturing and economic advantages, are suitable for high volume production of metal components and high material utilization, minimal scrap generation, reduced need for secondary machining operations, and lower cost per part compared to machining based processes. Now, let's look at the stress strain behavior in bulk deformation. Deformation occurs beyond the yield point in the plastic region of the stress strain curve. Material flow is governed by flow stress, which depends on temperature, strain rate, and material composition. To the effect of temperature, for odd working, lower forming forces, dynamic recrystallization, and no strain hardening. And for cold working, higher forces, improved surface finish, and increased strength due to work hardening. Now, let's look at the rolling process. What is rolling process? Rolling is a bulk deformation process in which a metal workpiece is passed between two more rotating rolls that apply compressive forces, resulting in a reduction in thickness and a corresponding increase in length. Rolling is the most widely used metal forming process in manufacturing industries. First, basic working principles. The workpiece is drawn into the roll gap by frictional forces between the rolls and the material. As the rolls rotate, the material undergoes plastic deformation. The thickness of the workpiece is reduced from initial thickness to final thickness. Volume remains approximately constant, so the length is increases. So the characteristics of rolling are deformation occurs primarily under compressive stresses, and it also can be performed as hot rolling or cold rolling. It's capable of producing large quantities of semi-finished and finished products, and also produces materials with directional mechanical properties due to grain flow. What are the products of rolling? Which is plates, sheets, and strips, structural sections like I-beams, rails, channels, bars, rods, and tubes, and also preforms for forging and extrusion. So this is the example of rolling process. Now, let's look at the principles of rolling. Deformation zone. The deformation zone is the region between the two rotating rolls where the metal undergoes plastic deformation. Within this zone, the material is compressed and its thickness is reduced while its length increases. The pressure exerted by the rolls varies along the arc of contact. First, let's look at the neutral point, which is also called as neutral plane. The neutral point is the location in the deformation zone where the velocity of the workpiece equals to the surface velocity of the rolls. Before the neutral point, the roll velocity is more than the strip velocity. Friction acts in the forward direction, pulling the material into the rolls. After the neutral point, the strip velocity is more than the roll velocity. Friction acts in the backward direction, and the position of the neutral point affects the rolling force and power requirements. For the draft is the reduction in thickness achieved in one rolling pass, which is defined as the initial thickness minus with final thickness. So the maximum possible draft depends on the coefficient of friction, roll diameter, and material properties. For spreading, refers to the increase in width of the material during rolling, which occurs mainly in flat loading of thick slabs, which influenced by roll friction, initial width to thickness ratio, and material characteristics. Now let's compare the hot rolling versus cold rolling. So what is hot rolling? Hot rolling is carried out above the recrystallization temperature of the metal. Under these conditions, the material undergoes dynamic recrystallization, allowing large plastic deformation with relatively low rolling forces. So let's look at the characteristics of hot rolling, which is lower loading forces and power requirements, no strain hardening due to continuous recrystallization, and can achieve large reduction in thickness in a single pass, and produces rough surface finish due to scale formation and lower dimensional accuracy and wider tolerances. So the applications are structural sections like I-beams and rails, and also thick plates, slabs, and blooms. So now let's look at the cold rolling. Cold rolling is performed below the recrystallization temperature of the metal, usually at room temperature. Since recrystallization doesn't occur, the material undergoes strain hardening. So let's look at the characteristics of cold rolling. Higher rolling forces required, increased yield strength and hardness, better surface finish and dimensional accuracy, and improved control over final thickness, and limited thickness reduction per pass. So the applications are thin sheets and strips, and automotive body panels, and appliances and packaging materials. So these are the examples and images of hot rolling versus cold rolling. So now let's look at the types of rolling. First, we have a flat rolling. Flat rolling is the most common rolling processes where the thickness of the metal slab, plate, or sheet is reduced using two or more rotating rolls. So the characteristics are produces flat products, which is plates, sheets, strips, and primarily reduces thickness, which may increase slightly due to spreading, and used in both hot and cold rolling, which is typically involves multiple passes to reach final thickness. So the applications are structural plates, sheet metal for automotive appliances and packaging, and coils for fabrication and fobbing. Moreover, we have a shape rolling. Shape rolling involves passing a metal workpiece through a series of rolls with especially contoured grooves to produce desired cross-sectional shapes. So the characteristics are produces complex profiles like I-beams, channels, rails, and it requires a sequence of rolls like breakdown, intermediate, and finishing. Has a high productivity and consistent dimensional and accuracy, and mostly perform as hot rolling due to large deformation required. So the applications are construction beams, railway tracks, angles, channels, and T-sections. Now let's look at the ring rolling. Ring rolling is a rolling process used to produce seamless rings by continuously reducing the thickness of a ring while increasing its diameter. So the characteristics are involves a driven roll and an idler roll, reduces wall thickness and increases ring diameter, and it's produce components with uniform grain flow and mostly carry out as hot rolling. So the applications are bearings, gears, flanges, and pressure vessel rings. Moving on to the next type of rolling, which is thread and gear rolling. Thread and gear rolling are cold rolling processes in which external threads or gear teeth are formed by plastic deformation rather than cutting. So the characteristics are material is displaced and not removed. It produces high surface quality and accuracy, improves fatigue strength due to favorable grain flow, and has a high production rates for small components. So the applications are bolts and screws, shafts with external threads, and automotive and machine gears. Now let's look at the roll forging. Roll forging is a process where metal is passed through a groove rolls that progressively shape the workpiece. So the characteristics are produce a near net shaped components, reduces forging load in subsequent operations, often used as a preforming step for impression die forging. So the applications are connecting rods, wrenches, and hand tools. So last we have a tube rolling and piercing. Tube rolling and piercing are used to produce seamless tubes by piercing as a solid billet and rolling it into a hollow shape. The characteristics are uses rotary piecing with angled rolls, which produces pipes without well seams and odd working process. So the applications are oil and gas pipes, boiler tubes, and structural tubing. So these are the example and images of the types of rolling. You may refer this. And then now let's look at the rolling mills. A rolling mill consists of a set of rolls mounted on bearings and supported by a rigid frame. The configuration of the rolls determines the type of rolling mill, which affects the achievable thickness reduction, accuracy, and production rate. First, let's look at the two-eye rolling mill, which consists of two horizontal rolls, can be non-reversing, which is one direction operation, and reversing, which is material passes back and forth. Simple design but limited thickness control. So the applications are roughing operations, blooming, and slabbing mills. The next, you have a four-eye rolling mill, which uses two small diameter work rolls supported by two large backup rolls. It helps to reduce roll bending and improves thickness accuracy. So applications for sheet and strip rolling and cold rolling of thin materials. Moreover, we have a three-eye rolling mill. Consists of three vertically stacked rolls, and the material is passed alternately in opposite directions. The eliminates need to reverse roll rotation. So the advantages are high productivity than two-eye mills and used for medium scale operations. And let's look at the cluster rolling mill, which consists of multiple backup rolls and surrounding small work rolls, and allows rolling of very thin sheets. The applications are hard materials and for precision rolling, for example, like stainless steel foils. Last, we have a tandem rolling mill, which consists of a series of rolling stands arranged in sequence. Material passes through all stands in one continuous operations, high speed and high volume production. So the applications are large scale sheet and strip production. So these are the measures and examples of the type of rolling mills, and you may refer to this. And then let's look at the typical rolling defects. Rolling defects are undesirable imperfections that occur due to improper rolling condition, such as uneven deformation, incorrect roll alignment, and non-uniform temperature distribution, or unsuitable material properties. These defects reduce product quality, mechanical performance, and dimensional accuracy. First, let's look at the waviness. Waviness occurs when compressive stresses exceed critical buckling stress. It appears as waves on the surface of roll sheets, which caused by uneven roll gap, non-uniform thickness reduction, and excessive rolling force. The effects are poor flatness and the appearance. Now let's look at the edge cracks. Edge cracks appear along the edges of the roll strip, which caused by the tensile stress at the edges, which are more common in materials with low ductility, excessive cold reduction, and improper temperature control. The effect is reduced strength and potential fracture. Furthermore, we have a zipper cracks. Zipper cracks develop along the center line of the strip, which occur due to high rolling speed, low ductility, and high tensile stress at the center, which affect severe structural weakness. So for last, we have center buckling, which occurs when the center elongates more than the edges, which results in buckling at the center region, and it caused by excessive crown, like thicker center, and incorrect roll pressure distribution. So it has effect of loss of flatness and dimensional defects. So what are the prevention of rolling defects? So it should have proper roll alignment and roll gaps control, and uniform temperature distribution, and appropriate reduction per pass, and selection of suitable rolling speed and lubrication. So that's all from me. Thank you.
Now I'm going to talk about forging. So what is forging? Forging is about deformation manufacturing process in which metal is shaped into a desired form by the application of compressive forces. These compressive forces are usually applied using hammers, presses, or specially designed dies. During forging, the metal undergoes plastic deformation, meaning the shape change is permanent but occurs without fracture. This is possible because the stresses involved are mainly compressive stresses, which metals can withstand very well compared to tensile stresses. Unlike machining, forging does not remove material, so there is minimal waste. Unlike casting, forging does not involve melting and solidification, so defects such as shrinkage cavities are avoided. As a result, Forging significantly improves the internal structure of the metal. The deformation refines the grain structure and aligns the grain flow with the shape of the component, which leads to superior mechanical properties such as higher strength and toughness. Next, the metallurgical advantage of forging. So forging provides major metallurgical advantages because of the intense plastic deformation applied to the material. During forging, the original coarse grains are broken down and refined, producing a fine and more uniform microstructure. This grain refinement directly improves important mechanical properties such as strength, toughness, and ductility. In addition, internal porosity and voids that are commonly present in cast products are closed and eliminated under compressive loading. Another key advantage is directional grain flow. During forging, the grains flow along the shape of the component rather than being randomly oriented. This grain alignment greatly enhances fatigue resistance and load bearing capability. Next, the classification by the temperature. So forging processes are classified based on the temperature at which deformation is carried out relative to the recrystallization temperature of the material. Temperature plays a very important role because it affects flow stress, required forging force, surface finish, and final mechanical properties. In hot forging, the process is carried out above the recrystallization temperature. Under this condition, dynamic recrystallization occurs during deformation, which prevents strain hardening. This allows larger plastic deformation to take place with relatively low forging forces. Hot forging is suitable for large component and material with high flow stress at lower temperature. However, oxidation and scale formation may reduce surface finish and dimensional accuracy. Next, warm forging is carried out at temperature lower than hot forging but above room temperature. It provides a compromise between reduced forming force and improved surface quality. Oxidation is lower than in hot forging and dimensional control is better. Cold forging is performed at or near room temperature. Since recrystallization does not occur, the metal undergoes strain hardening, which increases strength and hardness. Cold forging produces excellent surface finish and dimensional accuracy, but it requires very high forging forces and is limited to materials with good ductility. So what is open die forging? Open die forging is a forging process in which the workpiece is compressed between flat or simple shaped dies. The dies do not completely enclose the material, which allows the metal to flow freely in the lateral direction during deformation. Shaping is achieved through multiple strokes of hammer or press. Between these strokes, the operator controls the deformation by rotating and repositioning the workpiece. Because the metal is not confined within a closed cavity, dimensional accuracy is lower compared to closed die forging. However, open die forging provides excellent internal quality and soundness. This process is particularly suitable for large, simple-shaped components and is commonly used in low production volume. So I'm going to explain about the basic open die forging operation. So there is 4, which is offsetting, drawing out, cogging, and edging. So there are several basic deformation operations are used in open die forging, which is like I said before. Drawing out increases the length of the workpiece while reducing its cross-sectional area. This operation is widely used to produce shafts and rods. To ensure uniform deformation, the billet is rotated between successive strokes. Upsetting is the opposite of drawing out. It reduces the length of the workpiece and increases its cross-sectional area. This operation is commonly used to form bolt heads and flanges. However, excessive upsetting can cause buckling, especially in slender workpiece. Cogging is a repetitive drawing out process used to reduce large ingots into smaller cross-sections through successive compressive stops. And edging is used to redistribute material into specific regions of the workpiece, preparing it for further forging operations. So next, the barreling effect in upper die forging. Barreling is a common phenomenon observed during upper die forging. It is characterized by the outlet bulging of the sides of a cylindrical workpiece during compression. Barreling occurs mainly due to two reasons. First, friction between the die surfaces and the workpiece restrict metal flow near the ends. Second, temperature gradients within the billet cause the hotter central region to deform more easily than the cooler surface. As a result, deformation becomes non-uniform, forging loads increase, and internal cracking may occur. To reduce the barreling effect, proper lubrication and effective temperature control are important. So these are the product of upper die forging. The upper die forging is commonly used to manufacture large and heavy components where excellent internal soundness is required. Typical product including last shaft, turbine rotors, and rings. These components are often used in power generation, aerospace, and heavy machinery industries. Upper die forging is also economical for low volume production because it requires relatively low tooling cost compared to closed die forging. So now this is the forging equipment. Forging operations are carried out using either hammers or presses, depending on the size of the component and the required deformation characteristics. Forging hammers apply force through high velocity impact. The deformation occurs at high strain rates, making hammers suitable for smaller components and rapid shaping operation. Mechanical presses apply force through mechanical linkage and provide good control over deformation. They are suitable for high production forging operations. And lastly, hydraulic presses apply force gradually using hydraulic pressure and are capable of delivering extremely large forces. They are commonly used for open die forging of large components because they provide uniform deformation throughout the workpiece. Next, the forgeability of metals. Forgeability, you guys might be wondering what is forgeability. So the forgeability refers to the ability of a metal to undergo plastic deformation during forging without cracking or failure. Forgeability is influenced by several factors including material, composition, temperature, strain rate, and microstructure. Metals with high ductility and low flow stress generally exhibit better forgeability. Materials such as low carbon steels, aluminum alloys, and copper alloys have good forgeability and are widely used in forging processes. In contrast, high carbon steels and certain superalloys have poor forgeability due to their lower ductility and higher resistance to deformation, requiring precise control of forging conditions. And lastly, I'm going to talk about forging defects. Forging defects reduce the quality of performance and forged component. Common defects include lapse and fold due to improper metal flow, internal crack caused by excessive tensile stress, cold shut caused by incomplete bending of metal surface, and surface crack resulting from the overheating of ore oxidation. Buckling may also occur in long, slender workpieces under compressive loading. This defect can be minimized by proper control of forging temperature, deformation rate, and material flow during the forging process.
Now that we know about open die forging, I'll begin by introducing closed die forging, which is also known as impression die forging. Closed die forging is a metal forming process where heated metal is placed between two dies that contain impressions of the final component shape. When high pressure is applied, the material is forced to flow to conform to the die cavity. In terms of die configuration, we use an upper and lower die. As these dies close under high pressure, the workpiece material plastically deforms and fills the shape. Looking at the material flow, the metal experiences compressive loading, which causes it to flow smoothly into the impressions. This control flow is important because it aligns the grain structure with the part geometry, which in turn improves the mechanical properties. Finally, this process is usually carried out as hot forging. Forging at elevated temperatures actually reduces the flow stress, improves ductility, and helps prevent cracking during deformation. Now, when we do open die forging, there will be a flash formation. Flash occurs when excess material is squeezed out of the die cavity at the parting line, forming a thin layer known as flash. For reference, this is what the flash looks like. This is the excess material. This happens because the die cavity is slightly intentionally overfilled. This overfilling of the material is actually beneficial as it ensures that there is enough material available to fill all regions of the die impression, especially thin or complex sections. The flash itself is very thin, which means it cools rapidly due to its large surface area being exposed to the surrounding as you can see here. As it cools, it becomes more resistant to further deformation. This increased flow resistance at the flash restricts outward movement of metal to flow inward, ensuring that complete cavity filling. As a result, defects such as labs, voids, or incomplete fillings are minimized. So, although the flash looks like a wasted material, it actually plays a critical role in ensuring the forging quality. Now, here are some common parts made by closed die forging. Closed die forging is widely used to manufacture high strength engineering components. One example is the connecting rod, which are forced to withstand high cyclic stress and fatigue loading in internal combustion engines. Another important application is crankshafts. During the forging, the grain structure is aligned along the direction of the applied torque, which significantly improves the torsional strength and durability. Forged wrenches and hand tools also benefit from this process, as forging improves impact resistance and toughness, reducing the risk of sudden failure during use. And in the automotive industry, many components such as gears, levers, and suspension parts are forged to ensure high strength, reliability, and long service life under dynamic loading. Now, if we go further deeper, there is a technique called precision forging. Precision forging is designed to produce components with dimensions very close to the final required shape, significantly reducing the need for secondary machining. One major advantage is dimensional accuracy. Improved process control allows tighter tolerances compared to conventional forging methods. This is basically we fill the billet with the exact required amount so that when the both dies press together, there is no flash produced and the final product is near net shape. Although the tooling costs are high, the overall production cost is reduced in high volume manufacturing because less material is actually wasted and fewer machining steps are required. Another important aspect is process control. Precise control of the billet volume, as I said just now, and also temperature and die alignment is actually essential to achieve consistent and accurate results. Now, let's look at the types of precision forging that are available. There are several types of precision forging, each suited for a specific application. The first is flashless forging, where an accurately measured billet is used so that the material completely fills the die cavity without producing the flash. This results in minimal waste. Now, the next thing is near net shape forging, where the forged part closely matches the final geometry and requires only minor finishing operations, maybe such as machining, milling, drilling. Another type is isothermal forging. In this process, both the dies and the workpiece are maintained at similar elevated temperatures. So let's say the material is 500 degrees Celsius and also the both dies will be approximately the same temperature. This prevents rapid cooling, and improves material flow, especially difficult to forge alloys. Because of these advantages, precision forging is commonly used for titanium alloys and superalloys, particularly in aerospace application. Now, I'll discuss about upset forging and heading, which are closely related processes. Upset forging increases the cross-sectional area of a workpiece by applying compressive force along its axis. The force is applied parallel to the length of the workpiece, causing a localized thickening as shown as here. Common products made using upset forging includes bolt heads, fasteners, and valve components. Heading is a high-speed form of upset forging, used mainly for small components. It is widely used in the mass production of screws, nails, rivets, and bolts, where high productivity and consistency are required. As you can see in this diagram, this is the process of the heading process. Okay. Now, there are also other specialized forging processes. In addition to conventional forging, there are roll forging, which shapes metal by passing it between a rotating grooved rolls. This process gradually reduces the thickness and improves the grain structure. There is also skew rolling, which uses angled rolls to produce a spherical or cylindrical components such as bearing balls, as you can see here. Finally, there is also orbital forging, which deforms only a small area at a time using a circular die motion. This reduces forming force and is suitable for precision components. As you can see in the diagram, it is very similar to the jiggering process that we studied during the ceramic formation. It will rotate in a similar motion so that it's spinning in an orbital way and it's forging the material. The movement is similar to that process, the jiggering process. Now, finally, I would like to talk about the advantages and limitations of closed die forging. Forging offers several important advantages. Firstly, it provides high strength and toughness as continuous grain flow follows the part geometry. Secondly, forging offers excellent fatigue resistance, making forged components suitable for repeated and dynamic loading conditions. It also offers a structure. It also improves structural reliability by minimizing the internal defects such as porosity, which are commonly found in cast components, as we have studied before. Forging solves this issue by not having any porous materials. However, even though they have all these benefits, there is also limitations, which are forging or one limitation of forging is shape complexity, as complex internal cavities are difficult or sometimes even impossible to form using forging. Another limitation is the high tooling cost because of this, forging is the most economical for high volume production, where tooling costs can be spread over many parts. Okay. To conclude, forging, particularly close die and precision forging, plays a critical role in manufacturing high strength and reliable components across automotive, aerospace, and industrial applications. Despite higher tooling costs, the superior mechanical performance makes forging an essential manufacturing process. That's it from me. Thank you.
Good day everyone. In this presentation, I will briefly explain what extrusion is and discuss the fundamental principles and go through the different types of extrusion processes and also explain about the equipment, materials and common defects involved in extrusion. Okay, first, let's see what is extrusion. Extrusion is a manufacturing process in which the material is forced through a die opening to produce a product with a constant cross-section. This process is commonly used for both metals and polymers. Examples of extruded products include rods, tubes, pipes, channels, and windowed frames. One important point is that extrusion mainly involves compressive stresses, which allows large deformation without failure. especially for ductile materials. Okay, next let's see about fundamentals of extrusion. Okay, extrusion can be divided into hot extrusion and cold extrusion. Okay, in hot extrusion, the material is processed above the above its recrystallization temperature. This reduces the force required there and allows large deformation. However, dimensional accuracy and surface finish are usually lower. In cold extrusion, the process is carried out at room temperature. Although higher forces are required, the product has better surface finish, higher strength, and improved dimensional accuracy due to strain hardening. So the choice depends on the required properties and application. Okay, next, let's see about the stress, strain, and flow consideration in extrusion. Okay, during extrusion, the material experiences plastic deformation under compressive stress. However, friction plays a major role, especially at the container walls and die interface. If friction is too high, it can cause non-uniform material flow, leading to defects. That is why lubrication is very important in extrusion. Proper lubrication helps reduce friction, lowers the required force, and improves the surface quality. Okay, next, let's see about the extrusion ratio. Okay, the extrusion ratio is defined as the ratio of the initial cross-sectional area to the final cross-sectional area of the material. A higher extrusion ratio means greater deformations, higher extrusion force, and finer grain structure, especially in hot extrusion. However, very high extrusion ratios may also increase the risk of defects, so it must be carefully controlled. Okay, next let's see about types of extrusion process. In direct extrusion, also known as forward extrusion, the billet is pushed forward through a stationary die. The material flow in the same direction as the ram movement. This method is widely used because the equipment is simple and economical. However, friction between the billet and container walls are high, which increases the exertion force needed. Okay, let's see about indirect extrusion, which is in indirect extrusion, the die moves into the billet while the billet remains stationary. Here, the material flows in the opposite direction of the ram movement. Because there is no relative motion between the billet and the container, friction is significantly reduced, resulting in a much lower extrusion force and a better surface finish. The limitation is that the equipment is more complex and billet length is limited. Okay, next let's see about the impact extrusion. Impact extrusion is a high-speed extrusion process, usually performed at a room temperature. A punch strikes the billet, forcing the material to flow rapidly through the die. This process is mainly used for thin-walled hollow products such as toothpaste tubes, aerosol cans, and battery cases, especially materials that are made from aluminum. Let's see about hydrostatic extrusion. In hydrostatic extrusion, the billet is completely surrounded by a pressurized fluid. This eliminates direct contact between the billet and container walls, resulting in a very low friction. Hydrostatic extrusion is suitable for brittle materials and allows uniform material flow. However, the process is expensive and requires proper sealing. making it less common in the industry. Okay, next let's see about lateral and continuous lateral or side extrusion. In lateral or side extrusion, the material flows perpendicular to the ram direction. This method is mainly used for special profiles, but it has limited industrial application due to complex tooling. Continuous extrusion also sorry, continuous extrusion also known as the conform process uses continuous feedstock instead of billets. There is no billet length limitation, resulting in a high production rate. It is commonly used to produce aluminum wires, rods, and profiles. Okay, next let's see the extrusion equipment and materials. So we have the main components of an extrusion system, which includes a die and die holder, ram, hydraulic press, and container. Die design is extremely important as it controls product shape, surface finish, and material flow. Lubrication is used to reduce friction and die wear. Typical extrudable materials includes metals such as aluminum, copper, and polymers such as PVC and HDP. Okay, next let's look at the extrusion defects. Several defects may occur during extrusion. Surface cracking occurs due to excessive temperature or speed. Pipe formation is a central cavity formed due to non-uniform metal flow. And center burst, also known as chevron cracks, it's an internal cracking defect caused by tensile stresses at the center. And die wear leads to dimensional inaccuracies over time. Most of these defects can be minimized by proper process control and die design. So to conclude this presentation, extrusion is a versatile manufacturing process used for producing constant cross-section components. Different extrusion methods are selected based on the material, product shape, and production requirements. Proper control of process parameters helps improve the quality and reduces defects. So that's all from me. Thank you.